This is the screencast for the Monday, September 30th lecture that was canceled. So what we'll do today is go through the nature of the coupling constant that's present in signal multiplicity and proton NMR. To understand this concept, we need to talk about bond angles that occur between the neighbors. And so we'll introduce a couple concepts here, walking through how that arises. So our first leap question here is, what is the hybridization of the atoms of C3 to C4? So we can see that both C3 and C4 are showing 4 sigma bonds, so both of these are sp3, and so our answer is D. We have 2 sp3 hybridized carbons. For the C2 to C3 bond, we see that carbon 2 is a ketone, so it's a carbonyl, so it's sp2, and we said C3 was sp3. So for this one, we have B, sp2, sp3. And so what type of bond is between C3 to C4? That's a sigma bond. So as a consequence of the C2 and C3 bonds both being sigma bonds, which of the following statement is true? The answer is A. Sigma bonds have free rotation. And so when we draw this, that means we can represent, so the little squiggle there just means if we rotate about C2 to C3, that has the same structure, the same molecule. The difference between these are actually called conformational isomers. That's abbreviated conformers. So conformational isomers, if you're ever wondering, when things are drawn different, are they the same? Yes, they are. It's just due to bond rotation. So these arise from sigma bond rotation. So we can rationalize why the n+1 rule is useful in predicting what a given signal will look like. Again, recall that the nuclear spin state of the neighbor can be aligned or opposed with the magnetic field. So we were representing that as +1/2 or -1/2, or visually as an arrow up or down. So the splitting of the signal that you're looking at is due to both upfield, so that's towards 0, and downfield, away from 0 lines of the original signal. And so what is the magnitude as measured in hertz of those lines? For example, if you have a doublet, what the question is asking, what is this distance in hertz? And so that's reported as the coupling constant J. So if 2 signals are coupled, that coupling constant has to be the same for both of them. So if splitting is due to neighboring hydrogens, are the respective signals split equally? And so the answer is yes. And we'll look at that ketone 2-butanone, specifically related to this quartet and triplet signatures that we saw. So here's the proton NMR of 2-butanone. And so if we're just looking at the 3 unique signals, again, we have 3 unique sets of hydrogen in a ratio of 3 to 3 to 2. And that's what these numbers down here indicate. So the ratio, again, we call it integration. And so let's just go through this and assign the multiplicities. So the singlet belongs to those CH3 hydrogens. The quartet integrates to 2, so that's the methylene, and then the triplet belongs to the methyl group there. And what we're going to focus on is now looking at these chemical shift values. And as I said, we want to look at the distance between those. You'll find that for each unique signal, that distance will be the same. It will change, as we'll see a little bit later on in this screencast, but for the quartet coupled to the triplet, and in the reverse manner, the triplet coupled to the quartet, that line spacing is the same. And so again, that's called the coupling constant. And it's reported as J. So here's an expansion of the downfield quartet. Quartet meaning it has 4 lines in the signal. And that arises because there are 3 neighboring hydrogens. So we're going to look at these values here, 2.4868, 2.4685, 2.4501, 2.4318. So again, those are reported in ppm, but chemical or coupling constant is reported in hertz. So we have to do a little bit of math or conversion to get this line spacing. So that's the J value in hertz. So determine that magnitude, which is the difference between the lines. You subtract the downfield from the upfield. So if we're reporting those 4 lines here in decreasing chemical shift in ppm, all we're going to do to arrive at this answer is take 2.4868 minus 2.4685, and we get a difference of 0.0183. And so we're then multiplying that number by 400 megahertz, which is the operating frequency of the instrument. And so when you do that, you get 7.32. Then you do the same for the 2-3 relationship and the 3-4 relationship, and you'll see that overall these numbers are converging at about 7.3 hertz. So that means the distances between those 4 lines is 7.3 hertz. Now if we do the same analysis for the triplet, so triplet again has 3 lines, and that arises from 2 neighbors. And so we're looking now at these chemical shifts 1.0756, 1.0573, and 1.0389. So we have 2 values we're calculating, those distances. So there's the 3 lines decreasing chemical shift. Here's the difference, 0.0183 times 400 megahertz. That gets us 7.32, and again, it's about 7.3 hertz. And so notice the reciprocal relationship between the quartet to the triplet to the quartet. Since they are in the same spin system, their coupling is equal to 7.3 hertz. And so what if there's not free rotation about neighboring hydrogens? What factors then influence the magnitude of the coupling constant? So the magnitude, that distance between the lines in a signal, is dependent upon the dihedral angle of the signal of interest in the neighboring hydrogens. So a dihedral angle is defined by the intersection of two planes. And so we know that a plane is defined by 3 points. And so the 3 points for each plane are essentially our atoms. So if we're considering 2-butanone, and we draw the carbon backbone in the plane as a zigzag, so I'll highlight that in red here. So that carbon backbone is what's called a zigzag. And then we fill in all the hydrogen atoms using wedges and dashes to indicate sp3 hybridized tetrahedral geometry. The wedges, which I'll highlight in red, those are projected out towards you. The dashes highlighted in blue are going away from you. And then in green, just the regular bond line, that's in the plane. So we're going to analyze those different types of hydrogens, determine what planes they in, and then determine the angle between the planes. That angle then determines what the coupling constant is. So which of the following correctly categorizes the type of hydrogen atoms in the drawing? So in plane, we have 1, 2, so we can eliminate A and D. Towards us, those are the wedges. We have 1, 2, 3. So now we can eliminate C. B will be the correct answer. Let's figure out the ones away from us using the dash. There's 1, 2, 3. And so we see that B verifies that. So essentially what we want to do is determine what is the angle between the two planes as defined by HA, carbon, carbon, HB. So 4 atoms define the dihedral angle. And so remember that the dihedral angle is defined by the intersection of two planes. Those two planes would be HA, CC, and CC, HB. So to do that, we have to look down the axis of the carbon-carbon sigma bond. And the tool to use this is called a Newman projection. And so this is Professor Newman right here, who spent his career at The Ohio State University and came up with this way of analyzing molecules in a study of organic chemistry called conformational analysis. And again, that's looking at how things are drawn and determining these relationships. So the Newman projection has 3 components. The front carbon is drawn as these 3 lines. Then we have the rear carbon, which is drawn as a circle, and then those lines projecting away or out of it are the bonds to that rear carbon. So if we know that carbon has 4 bonds, what we see in the Newman projection as you're looking down, so that front carbon to the rear carbon, the fourth bond is down the axis you're looking down. So carbon 1, you have 1, 2, 3 substituents, and the fourth is the bond to the rear carbon. The rear carbon has 1, 2, 3 substituents. And so these are two different ways of drawing a Newman projection, where we're looking, down an sp3 to sp3 CC bond. So we're going to do it two ways from the 2-butanone. We're going to have C3 be the front, C4 be the back, and then we're going to do it the other way where C4 is the front and C3 is the back. And you'll see that when we fill in these atoms of these bonds, that the Newman projections look different. So the first atom that's listed again is the front carbon. That's the one closest to you. So we number 1, 2, 3, 4 carbons of the backbone. For this projection, we want to look down the C3 to C4 bond so that our eyeball is there. And then really what this requires is that from the zigzag, that you're basically rotating the molecule. So you're looking, instead of straight on the zigzag, you're rotating your eye 90 degrees and looking down a sigma bond. So in the Newman projection, again, carbon 3 is in the front. And this top line is going to belong to now this bond here. That's the carbonyl and then methyl. So we'll fill that in. And then the line to the left is going to belong to that hydrogen, meaning that the line to the right is going to belong to the HB hydrogen, which is projected out towards you. Now, if you look down to carbon 4, which is in the back, represented by the circle here, if we see that HB and HA are both projected, we see that the HB and HA are both wedges. So that means they're both projected out towards you. So this line in the back carbon has to be HA. And then the remaining bonds are both the hydrogens of the of the carbon 4 methyl group. So in the other Newman projection where we're looking down, C4 is the front. We see that the bond going down is going to be this hydrogen here. The bond projected out towards you, HA, is going to be to the left. And then the remaining hydrogen out to the right here is HA. So we know that HA and HB are on the same side, so HB in the back has to be down and to the left. And then the group that's going up is going to be the carbonyl and the C1 methyl group, meaning that down and to the right is the other HA. So you can see that depending on what sigma bond is in the, or what carbon's in the front and what carbon is in the back, these substituents will be in different positions in the Newman projection. And so that's important for determining the dihedral angle, which we can now state if we're looking at HA, C, C, HB is essentially this angle here. So that's what we mean by the dihedral angle. And so let's look a little bit more into this. We'll review these questions and then determine how the magnitude of that angle influences the coupling constant. So which of the following Newman projections correctly depicts looking down C3, which is the front, to C4, which is the back? So again, we're putting our eyeball here, where C3 is in the front, C4 is in the back. So we want to have HB to the right. So far HA, or choice A, is good, B is not, C is not, D is not. So essentially A is going to be the correct answer. The carbonyl group has to be up, which we see, and then this H, which is projected back, is going to be down and to the left. Because HB and HA are on the same side projected out towards you, we need to show that here, and we do. And then the remaining substituents on the back are the two hydrogens of carbon 4. And if we do the same exercise looking at C4 now, which is the front, C3 is the back, we see that HA must be to the top, to the left, and C is the only one with that. We said HB needs to be on the same side. And then the remaining substituents on 4 are the two hydrogens, which we see here and here. Then the carbonyl on the back carbon is going up. And then this hydrogen, which is projected away, is going down and to the right. So as a review, in the C3 to C4 Newman projection, HB and HA are on the right. And then in the C4 to C3 Newman projection, HA and HB are on the left. So that's two different ways of looking at the same molecule with the perspective changing based on the Newman projection. And so how do we ultimately determine that angle? So if we consider that there are 360 degrees in a circle, and we see in the front carbon there are 3 substituents. So 360 degrees divided by 3 gets an angle of 120 degrees here. And we're going to be sticking the substituents in the back carbon on there as well. And so those lines on the back carbon will bisect the lines on the front carbon. So that line bisects, we get 60 degrees. So if essentially we're taking the total 120, we're then bisecting that, and so this angle here is 60 degrees. So that tells us the angle between HA to HB running through the 2 carbon atoms is 60 degrees. And so that angle theta relates back to what's called the Karplus equation, which was developed by Karplus at Harvard, and he won the Nobel Prize in Chemistry in 2013 for this and related work on computational organic chemistry. And so the Karplus equation, which is shown here, when it's graphed, gives this curve. So the Karplus curve has the angle in degrees on the x-axis, and on the y-axis is the coupling constant. So that's J, and it's measured in hertz. So you can see some noticeable points. When the angle is 0, the coupling is 13 hertz. When the angle is 90, the coupling is about a little bit more than 2 hertz. And then when the angle is at the greatest amount it can be, 180, we can see that the coupling is then 15 hertz. We saw already from the prior exercises from the 2-butanone, we calculated a J value that was 7 hertz. So if we go over to the y-axis, we find 7 hertz, we come over to the curve, we draw a line down, you'll see that we're about 50 degrees. And so that's not exactly the 60 we would expect, but keep in mind that as that C3 to C4 sigma bond rotates, we're getting an average of all of those angles, and that gives us an average coupling constant. So if the dihedral angle we figured out was 60, it's at 60 degrees. Again, you're getting a lower value of 4 hertz, but again, experimentally we observe it as 7.3, and that's because, again, this bond is constantly rotating, and so among all of those different rotational angles, you're getting an average coupling. And so the average CSP3 J value is approximately 7 hertz. So the Karplus equation is an empirical description relating the angular dependence of the magnitude of the coupling constant J. Because sigma bonds have free rotation about their axis, you're getting this average. So again, this distance here and that distance there are the same due to the free rotation. But what happens if you do not have free rotation? How does that influence the coupling constant? The example we'll look at here is called 3,3-dimethyl-1-butene. And we see that between carbons 1 and 2 there's a pi bond. And we know that with a pi bond there is restricted rotation due to overlap of the p orbitals. So again, you have there's the sigma bond, you have these p orbitals. They each contribute an electron, so they form the pi bond, and that restricts the rotation. And so when we're looking at this molecule, 3,3-dimethyl-1-butene, our first approximation of the unique H sets would be or we would say 2, 1, and 9. So we would say this carbon has 2 hydrogens, so that's a unique set with a ratio of 2. This carbon has 1 hydrogen, and then these 3 methyl groups are equivalent at 9. So to a first approximation, that's fine. However, due to the restricted rotation of that pi bond, hydrogens HA and HB are not the same. And so we need to revise to a second approximation. Where we have 4 unique sets. And now those hydrogens on carbon 1 are both unique. So we have 1, 1, carbon 2, and then the 9. And so we want to understand why HA and HB are different. And that's due to their angular relationship to HC. So HA to HC is not equal to HB to HC, which is telling you the angles are different. So the coupling is therefore different. So how many neighbors does HC have? So overall there's HA and HB, so there's 2 neighbors. This carbon has no hydrogens. So overall there's 2 neighbors. So our first approximation, we would say HC, 2 neighbors, we get 2 plus 1, that's 3. So we would say HC is a triplet. But that's not technically correct because, again, HC to HA is not the same as HC to HB. If we consider those hydrogens on carbon 1 as being different, we would say that this is 1, that's 1. And so if we analyze them separately, then we apply the n plus 1. We would say, okay, there's going to be a doublet and a doublet. So rather than having a triplet, HC is going to be called a doublet of doublets. Because the magnitude of the coupling constant J is different for those relationships. So again, our first approximation, we would say HC is a triplet. If HA and HB angles were identical. So what is the dihedral angle indicated? HC to carbon, carbon to HA. Those lie within the same plane, and they're actually sort of in front and behind one another. So the dihedral angle between them is 0. HC carbon, carbon to HB. Again, they lie in the same plane, but they're on opposite sides of that pi bond. So their angle is 180. So due to that restricted rotation from the pi bond, which is again the overlap of the p orbitals, we have these 2 relationships. HC to HA is called cis. HC to HB is called trans, where the cis angle is 0 trans angle is 180 degrees. And so that's recapped down here. 0, 180 degrees. The carpless curve then shows different J values. So we set HC to HA is 0. We go to the carpless curve. Here is 0. That's straight up the y-axis. We see that that value is 13 hertz. So this is 13 hertz. And remember, because we're considering HA as its unique neighbor, one unique neighbor, 1 plus 1 equals 2. So that relationship is going to be a doublet. And we know that a doublet looks like two lines. And what we just found, that the distance between those lines is 13 hertz. HC to HB was 180 degrees. And so we find that on the curve. From the x-axis we go up, then we go over to the y-axis and we find that that's 15 hertz. So HB again is a unique neighbor of 1. 1 plus 1 is 2, so that becomes a doublet, where now that distance is 15 hertz. Because 13 and 15 are not equal, HC will be called a doublet of doublets with coupling constants of 15 and 13 hertz. So for the dihedral angle of 0, you get 13 hertz. For 180, you get 15 hertz. So the multiplicity cannot be a triplet, because 13 hertz does not equal 15 hertz. Because each neighbor is considered unique, they both lead to doublets, and overall this signal is called a doublet of doublets. So what does that look like? We first report the largest coupling, which is 15 hertz, and that's from C to B. So there's your first doublet. Now each of those lines is then showing the coupling from C to A, which was 13 hertz. So there's your second doublet. And then since each line has that, this is called a doublet of doublets. And so to recap, for a normal looking triplet, the distances between those signals would have to be the same. But since they're not, it cannot be a triplet, and we call it a doublet of doublets. Now another thing we have to consider, because HA and B were different in their relationship to HC, do HA and HB couple with one another, even though they're on the same carbon? So what's the angle between HA to HB? That's your normal bond angle, because that's sp2 hybridized. This is 120 degrees. So again, trigonal planar. This is a bond angle. Again, that's not a dihedral angle, it's just a bond angle. So if the bond angle is 120 degrees, how do HA and HB couple with one another? So at 120 on the x-axis, we go up and over, and so we would approximate HA to HB couple one another with a coupling constant of about 4 Hertz. So overall, when you're looking at the angular relationships to the neighbors, the CSP3 to CSP3, due to the sigma bond free rotation, that's generally 7 Hertz. However, when you have CSP2 to CSP2 due to the pi bond restricted rotation, you have to use the Karplus curve to determine the J value. This also holds true for rings, because you have restricted rotation in rings. That means dihedral angles are locked. And then you have to use the Newman projection to determine what those angles are. And then you go to the Karplus to determine the J value. So at this point, we've covered pretty much everything we need to know about proton NMR in terms of chemical shift, in terms of multiplicity, and now in terms of the coupling constant between spin systems that are coupled due to neighbors.